video, let's discuss how to find response in RL series circuit excited with DC voltage source. For that, let's consider a series RL circuit excited by constant DC voltage V as shown in this figure. Say at t is equal to 0, these switches get closed. So after t is equal to 0, that is t greater than 0, the circuit is closed. Initially, the switch was in on condition. Initial current through the inductor U of 0 is equal to 0. Now, in order to solve this problem by means of Laplace transform method, it is convenient to transform this network into transformed network, that is S-domain network. Now let's see how to draw this transformed network corresponding to this network. The equivalent network in S-domain corresponding to this network is obtained as this voltage become V by S, this resistor there is no change, this inductance become S into L, and current flowing through the circuit is I of S. After t is equal to 0, that is in general t greater than 0, this is the equivalent circuit corresponding to this T-domain circuit. Now into this circuit we can apply KVL. So the equation become V by S minus I of S into R minus I of S into SL is equal to 0. Taking I of S as common into this part. So I of S into R plus SL is equal to V by S. Further simplifying, we can obtain I of S as V by S into R plus SL. Taking L from this term, we can write this equation as V by L by S into S plus R by L. In order to solve this one, we need to do partial fraction expansion. Considering that one, we can write I of S as A by S plus B by S plus R by L. So in order to obtain A, we need to multiply this equation with S and equate S is equal to 0. So after solving, we can obtain A as V by R. Similarly, in order to obtain B, we need to multiply this equation with S plus R by L, and into that equation we need to substitute S is equal to minus R by L. Substituting, we can obtain B as minus V by R. Now we can substitute A as V by R and B as minus V by R in this equation. I of S become V by R by S and minus V by R by S plus R by L. Now we can find out L inverse in order to find the time domain equation I of t. Taking L inverse of this equation, we can obtain I of t is equal to V by R minus V by R e raised to minus R by L into t. Taking V by R common, this equation become V by R into 1 minus e raised to minus R by L into t. In RL circuit, the time constant tau is L by R. So considering that one in this equation can be written as I of t is equal to V by R into 1 minus e raised to minus 1 by L by R into t. That is V by R into 1 minus e raised to minus t by tau, where tau is equal to L by R. That is the time constant of this circuit. So this is the general equation corresponding to t greater than 0. Now let's plot the variation of inductor current, voltage across the resistor and the inductor voltage with respect to time. For that, let's consider this equation. As this is a series RL circuit, current through resistor is equal to current through inductor is equal to V by R into 1 minus e raised to minus t by tau, where tau is equal to L by R. And what is voltage across resistor? I into R. I is obtained as this one, into R gives V into 1 minus e raised to minus t by tau. Then how to obtain voltage across inductor? We know inductor voltage is L into di by dt. I we got it as v by r into 1 minus e raised to minus t by tau. Substituting and finding the derivative, we can obtain VL is equal to V into e raised to minus t by tau. Now we can substitute these three worst cases, that is 0, tau and infinity, in these equations in order to see the variation of these voltages and currents. So first of all, let's substitute t is equal to 0 in these three equations. Let's see what is happening. So as e raised to 0 is 1, 1 minus 1 is coming in these two equations. Therefore, corresponding to t is equal to 0, IL is equal to IR is equal to 0 and VR is equal to 0. Corresponding to this equation, e raised to 0, V is coming. So corresponding t is equal to tau, here the equation become V by R into 1 minus e raised to minus 1. Solving this part, 1 minus e raised to minus 1 become 0.632. Therefore, this equation become 0.632 V by R. Similarly, corresponding to VR, the equation become 0.632 times V. In this case, e raised to minus 1 into V. E raised to minus 1 is coming as 0.3678. Therefore, VL is equal to 0.3678 volt. Now we can substitute t is equal to infinity. Here V by R into 1 minus e raised to minus infinity is coming. E raised to minus infinity is equal to 0. Therefore, this equation become V by R. Similarly, VR become V. In this case, e raised to minus infinity is 0. Therefore, VL is equal to 0. Now let's plot these values in graphical manner. Here time is taken as x-axis. In this case, y-axis is I. So corresponding to 0, the value is 0. Corresponding to infinity, the value is P by R. And corresponding to tau, the value is 0.632 V by R. So here we can see that this curve is an exponentially rising curve. Similarly, in the case of this voltage across the resistor equation, it is again an exponentially rising curve. Corresponding to 0, its value is 0. Corresponding to tau, its value is 0.632 V. And corresponding to infinity, its value is V. So it is an exponentially rising curve. But in the case of inductor, the case is just opposite. So at t is equal to 0, the value is V, and at t is equal to tau, its value is get decreased to 0.3678 times the initial value, and at t is equal to infinity, this voltage becomes 0. So it is an exponentially decaying characteristics or exponentially decaying curve. So voltage transient across R is exponentially rising and voltage transient across inductor is exponentially decaying. When we are summing these two values, that is VR plus VL, we can obtain V, that is the applied voltage, in the case of RL series circuit. So when we are considering this equation, the transient component is V by R into e raised to minus t by tau. As it is e raised to minus t by tau, that component is exponentially decaying. That is, the transient component of current V by R into e raised to minus t by tau is exponentially decaying. As t increases, this transient part dies out and steady state current V by R remains in the circuit. That is the final value. Now we can define the time constant as the time required to rise the current through the circuit to 63.2% of its final value. What is the final value? V by R. So The time required to rise the response to 63.2% of its final value is termed as time constant of the circuit.